So, last time we introduced partial derivatives and proved some things about them. Most importantly, we proved this linear approximation. That if you have a function that has derivatives, then you can approximate that function by its tangent hyperplane, I guess you might call it if you're a geometry. Or you might call it linear approximation. So the precise theorem was, if you have a point interior to some set in Rn, a function defined on that set which has all of its partial derivatives defined on some small open ball centered at P, which satisfies that the partial derivatives of this function are all continuous at P, then it follows that the function itself is continuous. So if you have all of your derivatives defined plus a little bit, then you are in fact a continuous function. So in that sense, differentiability implies continuity, which it does. Of course, you've done a homework problem at this point in which you see that having derivatives defined does not imply continuity. It also gives you these functions eta 1 through eta n, where this n is the same as that n, which are all continuous at P, and which each send P to 0, but such that for every x, the difference between f of x minus f of p is given by this linear bit, sum of a bunch of derivatives at p times the difference between p and x, plus this irroton. And if you just rearrange that a little bit, you really see that it's linear approximation. F of x is f of p plus a bunch of slopes times the amount that the input changes, plus some irroton. So that we proved that last time, yes? On Monday? Okay. And it turns out that this condition that all the derivatives are continuous is really important. And I won't call a function differentiable if its derivatives are just defined. And in fact, one of the homework problems assigned Monday makes that mistake. That differentiable there doesn't mean differentiable. When I say a function is differentiable, at P, I'll only say that if all of its partial derivatives are defined in a neighborhood of P, and are continuous at P. That is, they're all defined on a small open ball container. So my goal today is the proof of the chain rule from Calc 3. And let's just try to, I'm going to start by just writing on the board what sort of thing the chain rule applies to. So the chain rule should take a function from R, I think M is the variable I'm using, it doesn't matter, from Rm to R, and if I post-compose that with another function g from some other high-dimensional space down to R, I should be able to take the derivative of that. And so, what does the chain rule say? Well, the chain rule in R1 is like really easy to remember. It says that like df soc g by dx should be like there's the shorthand you use to remember it. This is the same sort of thing, but this function f has many entries. So if you want to take this derivative with respect to one of the xi's, well, this obviously isn't, like something like that isn't going to be enough. One, because this g is representing like many outputs right now. So instead, the way to remember it is, it should be like the sum of all the different ways you can take the derivative of f with respect to one of its inputs, plug g into that, then multiply, I'm going going to use the same variables as in the notes. Multiplied by the corresponding derivative of that entry of G. So let's state the chain rule formally. I guess I need to talk about like functions from Rn to Rn. I haven't mentioned them yet, but it's not hard to. Let U be a subset of Rn, P be in the interior of U, and G be a function from U to Rm. Then G has component functions, G1 through Gm, where G of x is, well, there it is one entry at a time. Because our G should take values in Rn, so I can specify n numbers. I'll say that G is differentiable at P if each GK is differentiable at P. Everyone? And that's, I mean, exactly what it should mean to be differentiable. We'll just check one output at a time. So here's the theorem that I want to prove, the chain rule. Let U be a subset of Rn, let P be a point interior to U. Let's have all of the partial derivatives of all of the component functions of G be defined here. So I'm not assuming that G itself is differentiable, it just has derivatives that are defined. Let's also assume that G is continuous at P. I know that is an extra assumption. Just having derivatives defined doesn't imply continuous. You can have terrible functions that have derivatives. Let's let V be a subset of Rm. Assume that the image of G is contained in V. G of P is interior to V, and F from V to R is differentiable at P. So the full hypothesis of differentiability, I'll need that at for F. Then the ith derivative of the composition of F with G evaluated at P is the sum of all of the derivatives of F evaluated at G at P times the corresponding derivative of the derivative of the corresponding component function of G evaluated at P. So there's a statement. There's a lot going on in that statement though, right? I think it would be helpful to just do something that you did in Calc 3 immediately after learning the statement of the chain rule, and that's actually just take an example, write down all of the ingredients, and show how to use the chain rule to make a computation. So let's do that. So let's let G be the function from R2 to R2, given by G of x1, x2 equal to that. Let's let F from R2 to R be given by that. Then, well, if you expand out that sum in the chain rule, you'll see that the derivative with respect to x1 of F composed with G evaluated at any x1, x2 should be the force derivative of F, derivative of F with respect to the force variable evaluated at G1, G2, times the derivative with respect to x1 of G upper 1 plus the same thing, but those two entries are now 2's. All right, there's just what the chain rule says. This time K only goes from 1 to 2 because 2 is M. So let's try to write down everything. So if G is X, if that's G, then I guess G1 is x1 squared plus x2 squared. G2 is x1 times x2. Then what's D1 of G upper 1? 2x1. 2x1, because we'll treat x2 like a constant derivative with respect to x1. D2 of G upper 1? Is it 2x2? Okay. D1 of G upper 2 is x2. Yeah. So you take that, you treat x2 like a constant. The derivative of a constant times x1 with respect to x1 is that constant. Similarly, d2 of g upper 2 is x1. D1 of f evaluated at y1, y2. F, not G.
y1 times y2 times e to the y1. Wait. No, that's just y2 times e to the y1.
Yeah.
Okay.
Right. Treat y2 like a constant, take the derivative. What about d2?
e to the y1.
Yeah. Right, just by thinking in terms of calculus. And we've proven several derivative formulas, and you guys in the thing that you just handed me, I think, told me why the derivative of the natural exponential is the natural exponential again. So, you've actually proven all of the formulas that you just used. I think we've proven all of them. Did we prove the product rule?
Yeah.
Okay, good.
So, yeah.
Good. So do you think we also have a product rule for like multiplying multivariable functions? Yeah, and I think you could prove it just by thinking about it for one variable functions, because what is a partial derivative? You just let one variable change and treat it like a one variable problem. So you could just use the product rule to prove the multivariable product rule. Anyway, let's now use this to compute the derivative of the composition. So this will be the derivative of f1 evaluated at g1, g2, d1f evaluated at g1, g2, so that'll be g2 e to the g1. I'm not going to write of x1, x2 because I don't want to take up all of the space. Times the derivative of g upper 1. What's the derivative of g upper 1? What's d1 of g upper 1?
2x1.
2x1 plus d2f, so e to the y1, evaluated at g1, g2. So that's e to the g1 times d1 of g upper 2.
x2.
x2. And now we'll just keep expanding. What's g2?
x1 times x2.
Yeah. Then g upper 1 is x1 squared plus x2 squared times 2x1 plus e to the g1, so e to the x1 squared plus x2 squared times x2. And if I were interested in this as like a computational class, I would say, well, now let's simplify that. But I think you all know how to simplify that, like factor out some stuff. So there's the statement of the chain rule, and hopefully just walking it out in this one example is good for understanding what the statement even says. It doesn't tell you why on off it should be true. Like, I guess you could try to write out the composition and use like one variable chain rules to discover why the statement should be true, but I think I'm not going to do that. Instead, let's actually get to the proof of the thing. So let's try to do that. So let's prove the chain rule. And it'll be motivated by the proof of the chain rule in one variable. So if you remember the chain rule in one variable, we said, well, if you want to compute the derivative of f of g of x, apply linear approximation, the fundamental limit of differentiation, to f, evaluate that at g. Now try to take the derivative of that. You'll have this error term evaluated at g, so that's something that will be hard to understand, but it will be multiplied by something that will have a derivative that's defined, and you'll know that eta converges to 0, so it won't make any actual contribution in the limit you want to compute. And the proof will go similarly here. It'll just be more complicated because there are more variables. And that's kind of it. So let's try to prove the chain rule by using linear approximation. So the proof is going to follow from the fundamental lemma. The function f is differentiable at g of p. So I can appeal to the fundamental lemma of differentiation at g of p to see that there exists a bunch of eta functions, eta 1 through eta m. The reason for that m is hopefully because f goes from Rm to R. I hope it did. The statement's, I guess, pages ago. F went from a subset of Rm to R, so we're okay there. They're all continuous at g of p and evaluate at to be 0 at g of p, such that for every y in B, linear approximation works. So f of any variable, any y in B is equal to f of g of p plus the sum of the kth partial derivative of f evaluated at g of p multiplied by yk minus g upper k of p. Because there's just the difference in the kth entry between the variable we want to evaluate and where we're taking linear approximation. Plus a bunch of error terms, plus eta sub k of y times y sub k minus g upper k of p. So if I've done that correctly, all I've done is happily I've grabbed the copy that I forgot to staple before class, so I don't have a staple to contend with. But there's the statement of linear approximation. I think that I just plugged things in correctly. All right, the x's are now y's because I want x's to be like the things in the domain of g. So I don't want to overload my variables. So y's will be the things in the domain of f. Plus, eventually I'm going to evaluate at g, and y already looks kind of like g. That's not a good reason to choose a variable, but it's a reason. Nice. So there's just evaluating what f of y is. And I want to know what f of g of x is. So, I mean, you know exactly what I'm going to do. I'm going to replace y with g of x. So y sub k is going to become g upper k of x. If you do that, you'll wind up with the sum of all of these dk's of f evaluated at g of p times g upper k of x minus g upper k of p plus the sum of a bunch of eta k's evaluated at g of x times g upper k of x minus g upper k of p. Fair enough? That was just like resubstituting variables. And I want to take the derivative of this, right? Oh, well. I also said I would do one more thing. I should actually read what's written down. D upper k of f evaluated at g of p, that's just a constant, right? Let's not make it look fancier than it is. That's just dk. Let's just give that a name. That'll also help to, it'll help to reduce the weight of notation in the next step. And also will make it easier to remember when things are constant. Things that look simple will be constants. So that means that, so I want to compute the derivative. The derivative satisfies like an additive rule. So let's just try to take the derivative of each piece. What's the derivative of a constant?
0.
0. So this is now a sum of a bunch of constants times functions. So it means I can add up all of the derivatives of these things that are being added together. And that's a product of a constant times a function what's the derivative of this thing with respect to xi? Well, this piece is just like it's the derivative of g upon k, right? It's one of the things that one isn't allowed to talk about. What's the derivative of that with respect to x? 0. P is fixed, it's a constant. So cool, that last piece we can just take the derivative of. That'll leave the error term, but do you remember what we got when we tried to compute the derivative of the piece that came from the error term in one variable case? I'll tell you what, we'll work it out for the linear piece, we'll see what we get, and then we'll know what the error term has to be if the theorem is going to be correct. It'll have to be whatever the error in what we wrote down is. All right, so the linear term is now f of g of p plus the sum over a bunch of k's of things that look like dk times g upper k of x, minus g upper k of p. So taking the derivative, we see that the ith derivative of all of this stuff is going to be 0 plus the sum over all k's of dk, that's a constant, times di, because I'm taking the derivative with respect to the ith variable, of g upper k, and I'm evaluating at p, minus 0. Fair enough? Just by applying derivative laws and the fact that the derivative of g upper k with respect to xi is defined by assumption.
Why would that be it?
Say again?
Why would that be it? Why would it be W is the function. They switch the inputs from p to x. Oh, yeah, we're evaluating q. Okay,
Yeah,
cool.
right, because p is the only place where I know that g has derivatives. I've assumed that g has derivatives at p, and that's it. So like I've tried to assume as few things as possible. So that means I can't possibly talk about the derivative of g at an arbitrary x. I can only take the derivative of g at p. And so adding 0 doesn't do anything, subtracting 0 doesn't do anything. That is exactly the sum over a bunch of k's of, now while we expand that dk, so that's dk of f evaluated at g of p so I'm just re-expanding that out. I'm saying it's not a constant anymore. It is a constant, but I'm expanding out its full name, times d sub I of g upper k of p. Well, take a look at that and take a look at the statement of the chain rule. How does that sum in between differ from what we wanted to show the derivative of f composed with g is? So I wanted eventually to compute the derivative of f composed with g.
They're the same.
And we computed a piece of what f composed with g is. I computed the linear approximation of f at g. I took the derivative of that. And hopefully this is now given everyone enough time to look at the statement of the theorem. This is exactly what I wanted the result to be. So what do you think I'm going to try to show that the derivative of the error term evaluated at g is?
Big fat 0.
0. If I evaluate at p. How do people feel about that? Feel okay? Good. So this is exactly, well, I guess that's also like the next sentence. So if you guys were reading ahead, you would have gotten a spoiler. We will now, aim to show that the partial derivative of the error term exists and is equal to 0. So let's expand out the error term. The error term is, well, that stuff. So I'll set e of x, e for error, to be the sum from k equal to 1 up to upper m, eta k of g of x times g upper k of x minus g upper k of p. And now I have to actually do something complicated, right? Because what's the definition of a partial derivative? That's what I need to compute. It's, well, evaluate this at x equal to that, and take the derivative and plug in t equals 0. Like, that's the definition of the partial derivative. So I guess that means we have to actually do it. So I want to compute the derivative with respect to xi of the error term evaluated at p, which is by definition the derivative with respect to a single variable function of e of phi of t evaluated at t equals 0. I guess if you look on the first page, it's h instead of t, but what's in a name? So let's see. So this is the thing that I want to take like the limit of that as t goes to 0. So let's try to evaluate that. And well, let's just try to do that. Oh, well, all of these phi's should be phi sub i's. Fortunately, I'm only taking a derivative with respect to a single variable, so the notational inconsistency isn't too damning. And again, this is the shortcoming of like having 2 days since last lecture to really learn all the details in the proof, figure out the right way to present it, and then write it all down and go screw some things up. The ideas of the proof are coming through this time, though, right? Okay, good. So let's take let's try to compute this derivative. E of phi of 0. Let's walk that out. So what is phi of 0? What do you get if you plug in t equals 0? You just get the point p.
Yeah.
So let's expand this out. So this will be the sum from k equals 1 to n. Oh yeah, so I guess there's one more thing I need to do. So E of phi of 0. So I need to compute. That's one of the ingredients. So let's see. There's E. So E of phi of 0 should be E of p. What's eta k of g of p? What are the things we get to assume about the eta terms in linear approximation?
Oh, they disappeared.
They all disappear at g of p. Additionally, when if that x is p, then what's g upper k of p minus g upper k of p?
Definitely 0.
0. So that even tells you kind of why the derivative should be 0. It's like two things multiplied together, both of which are 0, which.
Oh, yeah.
But I mean, that's like kind of a bullshit reason. So, so that term is 0. So let's expand out this now that I know that E of phi of 0 is 0. So that'll be the sum from k equals 1 up to m of a bunch of eta k of g of phi of t times the other term, g upper k of phi of t minus g upper k of, well, p is phi of 0, so I'll replace that p with a phi of 0. All that divided by t. And I want to take the limit of that as t approaches 0. So let's try to do that, and let's do it one piece at a time. Oh, my timing's way off. I'm going to end stupid early. As t approaches 0, what does phi of t approach? It approaches phi of 0, but alternately that's
P.
p. By assumption, g is continuous at p, right? That's like, I haven't used that assumption for anything yet. G is continuous at P. So G of phi of T must approach G of P. These eta k's, where are they assumed to be continuous? G of P. Because I took linear approximation based at G of P. And eta k of G of P, what is that equal to?
0.
So, putting all this together, each eta k of G of P of T as T approaches 0, what does that approach?
0.
0. Aha. So let's look at the limit that we want to compute and get 0 at the end. It's a sum of a bunch of things, a thing which converges to 0 times another piece. Well, if one of those limits converges to 0, that just means the whole thing's 0, right?
No.
No, I need the other thing to at least be like bounded.
Yeah.
Oh. But let's look at the other piece. The other piece is G of phi of T minus G of phi of 0 divided by T. What does that converge to as T goes to 0?
0.
No.
Oh, wait.
So let me write that down. So that's G of as T goes to 0, what is that?
K partial derivative of G of P.
You have everything right except for some of the indexes. All right, so that's, I'm taking the derivative with respect to the ith
Oh,
derivative.
the I.
So it's the ith derivative of G upper K at P. So tell me again, what does that piece converge to?
DIGKP.
Yeah, it converges to that derivative. In particular, it converges. Convergent things are bounded. So on the other hand, the limit of G upper K of phi of T minus G upper K of phi of 0 divided by T, well, let's even write it out in more detail. That's the same as, right, d by dt of G upper K of phi of T evaluated at T equals 0, but that's exactly di G upper K of P. In particular, does that limit exist by assumption? Yeah, it does, right? We assume that we certainly can't apply the chain rule if we can't even take the derivative of one of the terms. That's a lie. You might be able to take the derivative, but there's no reason that you should be able to. This is partially the partial derivative of d sub I of G upper K at P, which exists by assumption. Thus, so let's write down the conclusion. And to do that, I'm going to flip back and gesticulate at this again. Where do all of the eta k of G of phi of T converge?
0.
Where does that piece converge?
Bounded.
Yeah, it converges even to something. But yeah, we don't even need that. So tell me, what is the limit as T goes to 0 of E of phi of T minus E of phi of 0 all over T? Yeah, because it's a sum of a bunch of 0 times bounded. Where like that's something that I wouldn't actually even want to see in your proof. You would just conclude that it's 0. So let's put that all together. So that means that the derivative of f composed with g at p, well, f composed with g is the linear term plus the error term. So that'll be di of mathcal L evaluated at p plus di of mathcal E evaluated at p. What's the derivative of math cal L?
The thing we want.
Yeah, yeah. Well, you know what the conclusion is going to be, right? It's the sum. Take the kth derivative of f, evaluate at g of p, multiply by the ith derivative of g upper k, evaluated at p, plus 0. Okay, so I should have given myself more space there if I wanted to add that extra line, if I had that second 0. Because that's exactly what we wanted. So, there are two things you'll notice here. Unless I failed to correct a typo, the theorem does not conclude that a composition of differentiable functions is differentiable, because I didn't have a composition of differentiable functions to begin with. But, I mean, what do you think? If I take a composition of nice functions, should I get a nice function at the end of it? Probably. And in fact, kind of you really should. So let's write down a corollary. So U be a subset of R and P be interior to U, and let all of the component functions of G be differentiable in a neighborhood of P. Let's let V contained in R be contained in R and assume that G of U is contained in V, G of P is interior to V, and F is differentiable on a neighborhood of P. Then for any I in the set 1 through n and any x in a sufficiently small neighborhood of P, the ith derivative of f composed with G at x is the same as we just wrote down, and the composition f sub G is differentiable in a neighborhood of P. And let's, before we even do the proof, let's just talk about why it should be true. So I guess first things first, so in any small neighborhood, so in a sufficiently small neighborhood of P, all of the hypotheses of the chain rule are satisfied, I think. So that means we can apply the chain rule for any x in a sufficiently small neighborhood of P, and we'll get this formula. And now we just need to know that that's continuous, because differentiable means the derivatives exist and they're continuous. Is G continuous? Is that one of the assumptions? Or is it a conclusion of something?
Yes.
Cool, explain.
If G is differentiable, then it's continuous.
Yeah, if you have a function whose derivatives exist and are continuous, then the function itself is continuous. So that's what differentiable means. Differentiable means the derivatives exist and they're continuous. No matter how much you want differentiable to mean, the derivatives exist. It means slightly more than that, because derivatives can exist and the function will still not be nice. So that's continuous. Is dk of f continuous? Why? So as long as this G winds up in a small neighborhood of P, then G of P, there is a small neighborhood of G of P on which f is differentiable. Part of differentiable is you assume that the derivatives are continuous. So we'll assume that dk of f is continuous on some sufficiently small neighborhood. What about d sub I of g upper k of x? Is that continuous? So let's just go through this. So it looks like here we have a composition of continuous functions. Is that continuous? Yeah, maybe we haven't proven it, but it's not so hard to prove. there's a continuous function. Is a product of continuous functions a continuous function? Yeah, you proved that in analysis 1, and it's the same proof. You also proved it in point set topology, and there you don't even have to modify the proof. You're working in a topology. You 3 took topology? Okay.
Supposed to.
Okay.
I did not. Sorry, I didn't know if you were pointing at me.
I was, but now I know you did. Is some continuous functions continuous?
Yeah.
Yeah, and that's the same proof as done in analysis 1 again. Hey, cool, that just means that this thing is continuous. That's all the differentiable means. So now that we've talked through everything, let's just try to make sense of what the various assumptions are even there for. So the first thing that I think I'll do is I'll try to come up with the neighborhood of P. And maybe it's even reasonable enough to draw a picture. So let's see. I know that G from U to Rm is differentiable on some neighborhood of P. So if there's, I don't know, I think I called it B1, containing BG is differentiable there. That maps forward by G. To G of B1. There's the point G of P. I know that there is some small neighborhood there. Maybe I call that point G. Where the function f is continuous. So it looks like where am I going to need to land? Well, I better start with things that are actually in B1 so that I can take derivatives of G. I better push forward to be a place where I can take derivatives of f. So maybe I want the preimage. So, and I want to be in both sets, well, I want to be in the intersection. So, let's let B2 be a neighborhood of G of P on which f is differentiable. I'll set B to be the intersection of B1 with the preimage of B2. Then, well, I guess you need to believe that the preimage of an open set is an open set. But that's the definition of what it means to be continuous from a topologist's point of view. If you want to check otherwise, I need to come up with an epsilon delta proof, but that's not so bad. So that's still an open set. It still has P in its interior. So at this point, at every x in this intersection, we satisfy all of the hypotheses of the chain rule at that where we take that point x instead of P and plug that into the chain rule. So all the hypotheses are still satisfied. So we can apply the chain rule and see that di of f composed with G is the sum of all k of dk of f evaluated at G of P times di of G upper k evaluated at P. By assumption, f and G are differentiable, so dk of f and di of G upper k are continuous. Since G is differentiable, G is continuous. That was a corollary of the fundamental lemma of differentiation. Right, because once you write down linear approximation, you just get handed continuity. Since G is differentiable, G is continuous. Therefore, di of f composed with G is a sum of compositions of products of continuous functions, and so it is continuous. Nice. So, since I have 4 minutes, let me say a few words about the homework assigned today. Because the homework is, in honesty, pretty light today, because I think I've been really heavy with the homework, because I fall into that habit really quickly. So I've done my best this time to be a little bit lighter. And hopefully you'll do something interesting. So who remembers what the directional derivative of a function is? What is the direction? What is the directional derivative?
It's the derivative in u vector.
Yeah, you like, instead of looking in just like a cardinal direction, I say I want to look in that direction and take the derivative. So that means take a function which starts at this point and travels linearly in that direction, and then take the derivative of g of that derivative. Take the derivative in the direction of v. Let's send it around p. But maybe you'll remember that there's also like this formula for the directional derivative from Calc 3 as like, so that's called dv of g at p. But maybe you also remember that that's the gradient of g at p dot. Where what is the gradient? It's just like the n-tuple of all of the partial derivatives. And the dot product is what you remember from linear algebra or possibly Calc 3. You will prove that for your homework. And this looks like, well, a derivative of a function composed with another function. So I bet you could apply the chain rule to get this result. So there's one of the bits of homework. And the other one is, if we're going to use this formula and we're going to prove it using the chain rule, we better actually satisfy all of the hypotheses of the chain rule. In particular, that function needs to be differentiable. I mean, you can still try to take partial directional derivatives for functions that have partial derivatives which happen to exist but aren't differentiable. Do you think that you should still get this formula happening? You certainly have no reason to believe it. And in fact, your homework will have you show that for the example that you've already walked out in the first homework assigned Monday. If you take that function, it has directional derivatives, but it has partial derivatives. But those are the only directional derivatives it has. If you take any other directional derivative, you'll find that the limit does not exist. So things can be bad. You really need to assume differentiability if you want to document derivatives intelligibly. Cool. So, I mean, I'll stop.